The city has just opened its magnificent Fabergé Egg Museum, a towering 100-story building with a single, priceless egg displayed on each floor. The higher you go, the more valuable the eggs become, with the crown jewel sitting at the very top. But here's where our story gets interesting. The world's most notorious jewel thief has her eyes on the prize. Security is impossibly tight, and these eggs are massive. Her only shot is to drop one out the window into her waiting truck below and rappel down before the police arrive. But here's the catch that transforms this from a simple heist into a mathematical masterpiece. She suspects the most valuable egg at the top won't survive a 100-story drop. Being pragmatic and mathematically minded, she decides to settle for the most expensive egg that can actually survive the fall. In the museum's gift shop, she finds 2 souvenir eggs, perfect replicas that are perfectly worthless for selling but invaluable for testing. The challenge: what's the minimum number of test drops needed to guarantee finding the highest floor from which an egg will survive, no matter what that floor turns out to be? Before you dismiss this as a simple start from the first floor and go up one by one until an egg breaks problem, consider this. Throwing replica eggs out of windows repeatedly is going to draw attention. Our thief needs the most efficient strategy possible. Let's walk through this methodically. You drop the first replica egg from the first floor. It survives. You try the second floor. Still intact. The third floor. Success again. You continue this pattern. 4th, 5th, 6th, floor by floor, methodically climbing the building. In the worst-case scenario, the critical floor, let's call it the breaking point, could be the 99th floor. This means your first egg would survive drops from floors 1 through 99, finally breaking when dropped from the 100th floor. You'd know with certainty that the 99th floor is your answer. Total drops needed, 99 tests. This method is foolproof but painfully inefficient. Surely we can leverage our second replica egg to dramatically improve this approach? Strategy 1. Here's where strategic thinking begins to emerge. Instead of testing every single floor, what if we used larger intervals? Let's try dropping the first egg from every 10th floor. 10th, 20th, 30th, and so on. Suppose our first egg breaks when dropped from the 40th floor. This tells us the critical floor is somewhere between the 31st and 39th floors, since the egg survived the drop from the 30th floor but broke from the 40th. Now we use our second egg to test floors 31, 32, 33, one by one until it breaks. In the worst case, we'd need to test all 9 floors in this interval. Total drops needed, 10. Testing every 10th floor plus 9, testing the interval, equals 19 tests. This is a massive improvement from 99 tests, but the mathematician in you should be asking, can we do even better? Let's try another strategy. Strategy 2. The breakthrough insight is this. There's no rule that says every interval has to be the same size. Let's explore this with a simpler example first. Imagine we had only a 10-story building instead of 100 stories. We could test this entire building with just 4 drops using a brilliant approach. Drop 1. Test from the 4th floor. If it breaks, use the second egg to test floors 1, 2, and 3. At most, 3 more drops. If it survives, drop 2. Test from the 7th floor. If it breaks, use the second egg to test floors 5 and 6. At most, 2 more drops. If it survives, drop 3. Test from the 9th floor. If it breaks, use the second egg to test floor 8, 1 more drop. If it survives, the answer must be the 10th floor. Notice the pattern? The intervals are getting smaller. First interval covers 4 floors, second covers 3 floors, third covers 2 floors, and the final covers 1 floor. The key insight: we want each possible scenario to require the same maximum number of drops. This creates perfect mathematical balance. This leads us to a beautiful mathematical relationship. If we denote our first test floor as n, then our sequence of test floors should be n, then n plus n minus 1, then n plus n minus 1 plus n minus 2, then n plus n minus 1 plus n minus 2 plus n minus 3, and so on. This creates the mathematical equation n plus n minus 1 plus n minus 2 plus n minus 3, and so on, up to plus 1 is greater than or equal to 100. The left side is the sum of the first n natural numbers, which equals n multiplied by n plus 1, divided by 2. So we need n multiplied by n plus 1 divided by 2 is greater than or equal to 100. Solving this equation, n squared plus n is greater than or equal to 200. This means n squared plus n minus 200 is greater than or equal to 0. Using the quadratic formula or trial and error, if n equals 13, then 13 multiplied by 14 divided by 2 equals 91, which is too small. If n equals 14, then 14 multiplied by 15 divided by 2 equals 105, which is perfect. Here's the elegant strategy that guarantees success in at most 14 drops. Test floors 14, 27, 39, 50, 60, 69, 77, 84, 90, 95, 99, 100. Let's trace through the logic. Floor 14. If the egg breaks, test floors 1 through 13 with the second egg. 14 total drops maximum. Floor 27. If the egg breaks here, having survived floor 14, test floors 15 through 26 with the second egg. 2 plus 12 equals 14 total drops maximum. Floor 39. If the egg breaks here, test floors 28 through 38 with the second egg. 3 plus 11 equals 14 total drops maximum. The pattern continues, with each interval being exactly one floor smaller than the previous, ensuring that regardless of where the breaking point actually is, we never exceed 14 total drops. The complete 14-drop procedure. Step 1. Start with floor 14. If it breaks, use the second egg on floors 1, 2, 3, up to 13. If it survives, continue to step 2. Step 2. Move to floor 27, 14 plus 13. If it breaks, use the second egg on floors 15 through 26. If it survives, continue to step 3. Step 3. Move to floor 39, 27 plus 12. If it breaks, use the second egg on floors 28 through 38. If it survives, continue to step 4. This pattern continues until either the first egg breaks, then systematically test the remaining interval. The first egg survives all tests up to floor 100, meaning the answer is floor 100. Could we possibly do better than 14 drops? The answer involves a beautiful proof using combinatorial analysis. With k drops available, we can distinguish between at most k, choose 2, plus k, plus 1 different scenarios. Here's why. With the first egg, we can make at most k drops before it breaks. For each number of drops I with the first egg, from 0 to k, we have k minus I drops remaining for the second egg. This gives us k choose 2, plus k, plus 1 total distinguishable outcomes. For k equals 13, 13 choose 2, plus 13, plus 1, equals 78, plus 13, plus 1, which is 92 scenarios. For k equals 14, 14 choose 2, plus 14, plus 1, equals 91, plus 14 plus 1, which is 106 scenarios. Since we need to distinguish between 100 different possible floors, plus the case where eggs never break, we need at least 101 distinguishable scenarios. Therefore, 14 is indeed the minimum number of drops required. What if we had 3 eggs instead of 2? With 3 eggs, the optimal solution becomes significantly more complex but follows similar principles. The minimum number of drops reduces to approximately 9 for a 100-floor building. What about 1,000 floors with 2 eggs? The solution scales to approximately 45 drops using the same formula, and multiplied by n plus 1, divided by 2, is greater than or equal to 1,000. Most people initially gravitate toward the fixed interval approach, every 10th floor, because our brains prefer uniform patterns. The variable interval solution feels uneven and counterintuitive. This reveals a fascinating cognitive bias. We often mistake mathematical elegance for mathematical efficiency. The most beautiful solution isn't always the most optimal one, and the most optimal solution often requires us to embrace asymmetry and imbalance. The egg-dropping problem transforms a simple optimization question into a masterclass in mathematical thinking. It teaches us that 1. Intuitive solutions aren't always optimal. The obvious approach of testing every floor is the worst possible strategy. 2. Balance through imbalance. The optimal solution achieves perfect balance by using deliberately unequal intervals. 3. Mathematical proof prevents overconfidence. Without rigorous analysis, we might never discover that 14 drops is truly optimal. The next time you face a complex optimization problem, whether in code, business, or daily life, remember the egg-dropping puzzle. Sometimes the most elegant solution requires embracing asymmetry, and sometimes the most efficient approach feels counterintuitive.